Hi, this is the Music Tone Analyzer by Cedric, Ella, and Raoul. The purpose of this project is to parse tones from audio inputs, transforming it into frequencies ranging from C4 to B4, which is about 261 Hz to 493 Hz, using the Fourier transform, and displaying it to the users. We will be using a piano for demo purposes, and in order to achieve this functionality, we use the SparkFun electronic microphone breakout. The connection from our board to the microphone is a VCC of 3.3 volts, ground, and for the audio, we use port E3, which is equal to the ADC channel 0.
Okay, so for the input from our microphone breakout, we're going to need to do some analog to digital conversion. We're using the TM4 Launchpad, the TIVA series analog to digital converter on the board. We're using ADC sequence 1, which takes 4 samples when it's called to trigger the ADC. These 4 samples are going to be averaged to limit our noise and give us better data on each sample. We're going to get 1,024 of these samples and to be processed by our Fourier transform. So for our Fourier transform, we're using code given by Valvano, starter project, profile FFT 4C123. Fourier transform function in there takes 1,024 samples, and it changes them from the time domain to the frequency domain. Our frequency domain data will take the index of our highest sample and times that by our frequency bins to get the resulting frequency of the note played and display the note on the serial terminal. So here's our picture of our original code. As you see, we're doing the ADC conversion first, getting those samples. We have a delay of about 20 microseconds in there at the end of each sample. Then we do the Fourier transform on it and print out this frequency that we found.
Okay, so the conversion from the while loop to RTOS was basically just breaking the code down into its 3 main components and placing them in 3 separate tasks. The first task was acquiring the ADC data. Task 2 was the processing of the data, and task 3, our serial terminal task, was printing that final note to the UART terminal. For the first task, however, we needed a very short and very precise delay, so we still had to use a version of the system control delay instead of the inbuilt task delay because we wanted a delay that was on the scale of around 20 microseconds, and the shortest that Microvision RTOS could provide us was a millisecond long. So we created a new BSP task that could access that original system control delay. So the switch to 80 millihertz clock from a 16 millihertz one did change the data acquisition process a bit because we were using the same delay even though the instructions were now being processed 5 times as fast, but we didn't really feel the need to adjust that number because the new delay just created a shift in the bins. So it was easier to just map the bins to these new values than to try and correct the note by messing around with the delay. For instance, C4, it was just moved from bin 9 to bin 13, so we just had it so that the if statement corrected for that instead. Here's a picture of our RTOS code, our 3 tasks, and the BSP delay function we added to the BSP system file. And as you can see, these tasks greatly resemble our initial round-robin while loop code, just broken into pieces.
So here's our music tone analyzer. As you can see, we have the piano set up. We can play our notes. It's going from C4 over here all the way to B4. So when we play a note, C4 you see on the serial terminal, shows up D4, E4, F4, G4, A4, and B4. And we can also play in different orders just to show you it's not just stuck on one note. Yeah, you can take in any of these notes. We also tested with pure tones, but we're only going to be showing the piano here.
Thank you.